What was the first thing we begin with under indices, powers, exponents? What's the definition of an index? If I wrote a to the power m, what does that even mean? So a to the power m is defined as a times and so on a m times. I don't know how many times m is, but it can be 1 or 10 or 100 or whatever else. We can now take this idea and we can build on this. If we have two numbers like this, a to the power m and a to the power n, then a to the power m times a to the power n is equal to a times a m times a times a n times. And that gives us a to the power m plus n. That is what we call an index law. And if we do division, n to the power m divided by a to the power n, we get a to the power m minus n. And if m is equal to n, you get the following: a to the power 0. And then we have said that must be equal to 1. That was the last law we have established. Then we can raise the next question. We have said that for any number x, x to the power 0 is equal to 1. 0 to the power of any number is 0. So what we have here is that x to the power 0 is equal to 1 and 0 to the any power m is equal to 0. So what happens when you put these two together? If you approach from the right equation, you can say it should be 0. So 0 to the power 0, it should be 0. If you approach from the left equation, you can say it should be 1. So is it either of those two, or is it something different entirely? We can observe the following table. With this, I'm trying to establish a pattern. As you see, the numbers are getting smaller and smaller. I'm trying to get to 0 to the power 0, so I'm getting closer and closer. If you had to guess at this point, you would think that when we get to 0 to the power 0, it is going to be 0, as the numbers are dropping. So the numbers are decreasing, but not much. For 0,6 and 0,5, the numbers are close together, and they are even closer for 0,5 and 0,4. So the numbers are decreasing, but they are slowing down. So what we are looking at seems to be an exponential decay. If we continue and put the other values, we get that the slowing down is not even the slowing down. It's gone the other way, so now we are climbing again. So I'm getting closer and closer to 0 to the power 0, and all up to number 0,4 to the power 0,4, numbers were decreasing. And as we have approached 0,4 to the power 0,4, we were slowing down. These gaps were getting very, very small. But now that we went from 0,3 to the power 0,3 and continue on our way to 0 to the power 0, the gaps started to get bigger. So this gap is 0,027 and the next one is 0,069. At this point we need more numbers. So let's look at 0,05. Which is 1/2 of 0,1. Now we are slowly going towards 0 to the power 0, but in small chunks, and I want to get there faster. So let's see what happens with 0,001, which is 10 times smaller than the previous number. Let's go 10 times smaller again, so we have 0,00001. The next one is after comma, 4 zeros and then 1. So let's see what happens with 5 zeros and then 1. If you go far enough with the calculator, it will finally give the answer 1. But we have done two things. First, we have seen it to drop down, but then it has turned around. It has started to increase. But then it didn't increase forever. So we never got to 0. What it seems to be going towards is 1. So it seems to be that 0 to the power 0 is equal to 1. That's the best we can say. So what we were doing with these calculations was that we were taking a limit of a function f of x is equal to x to the power x when x was approaching 0 from the side of positive numbers. The limit is this idea in which we are approaching a certain number. We can never get there, but we can get very close to it. This is written as a limit when x approaches 0 from the side of positive real numbers from the function x to the power x, and we got that approaches 1. It never gets there, but that is where it is going. If it could get there, that is what would happen. So this to a certain degree gives you a conclusion. And one more thing to answer is, why does this function turn around between the dots 0, 4 and 0, 3? And at which dot exactly it goes from decreasing to increasing? So we can observe this function f of x, which is defined as x to the power x. We need to find the derivative of this function, f prime of x, which is equal to x to the power x, and then derivative of that. This is complicated to calculate, so we are going to use an ln function to help us do this. So ln of f of x and then derivative of that is equal to 1 over f of x, as the derivative of the ln of x is 1 over x. We have a composition of two functions and we are doing the derivative of a composition. So this is going to be multiplied by a derivative of the function f. F derivative is then equal to f of x times an ln of f of x and then derivative of that. So ln of f of x is equal to ln of x to the power x, which is equal to x times ln of x. Now the derivative of this ln of f of x is equal to x times ln of x and then derivative of that. Derivative of this product is equal to ln of x plus x times 1 over x, which is only 1 plus ln of x. Derivative of f is then equal to x to the power x times 1 plus ln of x. Derivative of f is equal to 0 if and only if x to the power x is equal to 0, or 1 plus ln of x is equal to 0. X to the power x is equal to 0. This can't happen for positive real numbers. This other part is equal to 0 if and only if ln of x is equal to negative 1. So e to the power ln of x is equal to e to the power negative 1, and that means that x is equal to 1 over e. That means that at the dot 1 over e, function f of x, which is defined as x to the power x, has a local extreme value. So this is what the derivative of function f behaves like in the neighborhood of the dot 1 over e. We are looking at the dot 1 over e on the segment from 0 to 1. For the input from 0 to 1 over e, it gives a negative output. For the interval from 1 over e to positive 1, it gives a positive output. So a function f on the interval from 0 to 1 over e decreases as the derivative gives negative values. And on the interval from 1 over e to 1, it increases as the derivative gives positive values. So a function f at the dot 1 over e has a local minimum value. Now this 1 over e is equal to 0,36787,944 and so on. Dot 0,4 is on the right side of it, and the dot 0,3 is on the left side from it. And finally, I will show you the graph of a function f of x is equal to x to the power x. I will talk more about analyzing the functions in my calculus lectures. So thank you for watching. Please like, share and subscribe and leave a comment. I'll see you in the next video.